Well, hi everyone. Welcome back. Welcome to our Management Science course online, week 5. And I have a couple of things to remind you about. There is a new graded assignment, number 2, just posted on Canvas today. It is due on Monday, the 12th of July. It's worth 2.5% of your course grade. And the problem assigned is from Chapter 2. It's problem number 33, Part A only. It's going to help you with some upcoming Chapter 14 work. That's why I'm assigning this as part of Chapter 2. You're going to be using graphical method to solve an optimal solution. And I want you to scan or photo your work and post it to Canvas. And I've got more instructions there on the assignment tab. So please reach out to me if you've got any other questions related to this assignment. And also, additionally, I wanted you to be reminded of the team project planning. I have created the pairings, the links under week 4 module. I recommend that you reach out to your teammates soon. We've got 5 and well, actually, we've probably got 6 weeks or so until this is going to be due, and you're going to be able to choose from a variety of topics, whichever you think appropriate. We've only gone through chapters 2 and 3 so far, but you can choose from any of the chapters that we're going to work on in the next several weeks. So just a reminder, reach out to your teammate soon and just make contact. Okay, so let's finish up some Chapter 3 definitional items. I'll walk you through one of the practice problems I asked you to be prepared to work on this week. So a couple of definitional things I want to review. And the interpretation of dual values or shadow prices relative to something we call relevant costs or sunk costs. This is just definitional. For us, everything we do assumes sunk costs. But let me walk you through these anyhow. This is explained on page 108 of the text, and it really revolves around how much money are you willing, or how should you look at this, to pay for one additional unit of resources. In other words, cutting and dyeing time, sewing time, inspection and packaging time. You use those kinds of considerations when you're considering whether to add more staff or whether to add overtime, so on and so forth. So 2 distinctions relative to this: relevant cost or sunk cost. And I remarked just a moment ago that everything we work on we're going to consider as sunk costs. But let's look at these definitions, because you might treat them differently if you were to set these up in the real world. So we look at a resource, the cost of a resource, like sewing time, as being a relevant cost if the amount we pay for it is dependent on the amount of the resources needed by the decision variables, needed by producing a standard bag or a deluxe bag, that sort of thing. So, for instance, if Par Inc., who makes those standard and deluxe golf bags, only had to pay employees for hours worked, right, that they wouldn't have to incur the costs of slack time. We have some extra time in a couple of our variables, then we would call this relevant costs. And if you have that, you only had to pay for the actual time work, these should be reflected in the objective function coefficients, and you would treat them differently. You would treat them fractionally. We're not going to treat it this way. The simpler and easier way for us at our level of learning is to treat them as a sunk cost, as if we had to pay for these costs regardless of how much those resources would be actually used. And again, we don't reflect those sunk resource costs in the objective function coefficients. We just take those objective function coefficients, say the 9 and the 10, that is $9 of profit or $10 of profit. We just take them at face value, if you will. So we're assuming sunk costs in every case. And again, in that case, when we treat them as sunk, the dual value is defined as the maximum amount you should be willing to pay for one additional unit of the resource. That is, if you had to make a decision about how much any extra hours to add, how much overtime to pay, and so on, this would give you an indication of how much that should be worth to you. Now, you may pay something different. You may pay a premium. Now, if we treat the resource cost as relevant, we're only paying exactly for what we're using, not paying for any slack time, then we treat the dual value as something as a maximum premium over normal costs we should be able to pay. It's a little bit of of splitting hairs, but it does make a difference in some of the ways you set it up. But we're going to keep it simple and straightforward and treat everything as a sunk cost. All right, some other considerations we need to be aware of. Classical sensitivity analysis for most computer packages, like we're using in Excel, have limitations. And one model cannot be used typically to solve multiple recommendations. We often have to use a series of scenarios and changes. And when we go through the practice problem we're going to examine for this chapter, and that you should use as your preparation for the test on Chapter 3, you're going to treat it that way. You can only do one thing at a time. And that falls into this notion, I mentioned it last week, about simultaneous changes. So when we, for instance, when we change the right-hand side constraints, adding more sewing hours or inspection and packaging hours, we can only change one at a time. And we have to resolve the model every time we make a change. So similarly, if we have changes in the coefficients of the constraints, that is, how many sewing hours does it take to prepare a standard bag? It's half an hour in our case. Say we change that to be, it takes more time, 3/4 of an hour. We would have to change that one at a time as well. So it's not perfectly and optimally efficient. But again, the higher order software packages that you can buy will allow you to change things simultaneously. Not the Excel tools we're doing, certainly not any manual methods. Okay, so that is the last of the definitional items for Chapter 3. So let us pick up from where we left off last week. I asked you to consider doing this as an at-home practice problem, whether you had the opportunity to do so or not. It's okay if you did not. And I asked you to take the solution from the PowerInk problem that was resolved, and this is the sensitivity template completed. And I'm going to pull that up in a minute, and then answer these questions. And I put this language in there about restoring all base values for each question. That comes back to what I just mentioned about the can't make simultaneous changes, have to make it one at a time. And I'm going to point that out in every case. I want you to realize that. So these are the 6 questions that I posed for you last week. These are now the answers, and I'm going to show you how we arrive at each of those. These are the answers to each of these problems. And these are examples and similar to the types of questions I'm going to ask you in the test associated with Chapter 3. These are all what-if type questions. What if PowerInk increases, etc., etc.? What if they decide to do this or that? What effects, or what are the outcomes? And again, I'll walk you through each of these, but these are the answers, so you have them, and I'm also going to walk you through the particular problem itself. So let's go through that. Now, this is the file that I had posted for you called Template Completed, and then I have another version, and I called it Template Completed with Questions, where I added these questions, the 6 questions from the screen I just showed you in PowerPoint, and I have added them to this file so that we can walk through them one at a time. And so I also put this reminder, restore all base values before each question. That is, when we do question 1, we're going to make some changes in the cells here, and we're going to want to restore it back to its original value so that we can answer question 2 and so on. That's what I mean by restore all base values before each question. Okay, let's consider question number 1. And again, let me also remark that this is the completed file. This is what I walked through with you last week, how to complete these blue cells to be completed by students. I walked you through that last week. Use the sensitivity report data, put it into the solution, put these values in. Once you've done that, then you can answer the what-if questions. So let's look at question number 1. If PowerInk, the company we're considering, increases the available finishing time to 788 hours, how much will its new total profit be? Notice that finishing currently is limited to 708 hours. The shadow price or dual value of each hour of finishing is identified as $6.94. Now, with 708 hours, you can see that the total profit is 76.68. This is the optimal solution currently. But if PAR Inc. were to make more time available, and I'm going to change this cell right now. I'm going to color it red so you can watch me change it. Change it from 708 to 788. And I were to rerun Solver, I'm going to get a new number. I get a maximum total profit here, maximized total profit of 82.23. That's my new answer. That's the answer to number 1. You could have done this also in a slightly different way. Let me return this to 708, rerun Solver, take it back to the original values. I could have said that, while my profit is 76.68 now, each additional hour of finishing up to a maximum of 900 will garner me additional profit of $6.94 per hour. So I could have said, and I'm going to put an Excel formula in here, I could have said, well, what is from 708, if I went to 788, that's 80 hours additional. What's 80 times this value, 694? That's 555. And what is that value of 555 plus the original profit? 82.23. Same answer we just got a moment ago. I had showed you 2 different ways to arrive at the answer. First way was to change this value to 788 and rerun Solver. Second way was to leave this at 708 and recognizing that up to 900 hours can be added. If you went to 901, it becomes a different level of consideration. It's outside of our range of feasibility. But if we leave it at lower than 900, we went to 788. That means 80 additional hours. Each hour brings us $6.94 of additional profit. If we added that 80 times 694 plus 76.68, we would also get 82.23. That's the answer I gave you on that slide. Okay, let's go to question number 2. Question number 2 asks us, to what level or number can PAR Inc. decrease its standard bag profit and still maintain the same optimal production levels? Well, remembering that, again, this pertains to the standard bags, we're dealing in column B. We previously identified that there was a range of optimality. The range of optimality is the range with which we can change the selling or the profit contribution, in this case per bag, from $6.31 up to $13.49. And if it's within that range, these values here, the same optimal production levels, 540 and 252, will remain the same. So the quick answer to our question, it can decrease its standard bag profit and still maintain it, is this value right here, the minimum, the low end, $6.31. So let's prove that. Let's change this value to 6.31. Let's rerun Solver. You can see that it stayed at 540 and 252. Just for kicks, let's make this 6.30. We're going to go below the range of optimality. Rerun Solver, and oh, look what happened. The optimal solution changed. So we don't want that. We know, I just proved to you that if I go outside that range of optimality, my optimal production levels change. Let's restore this to 10. Put this back to the original values, rerun Solver, bring everything back to where it was. Okay, question 3. If PAR Inc. decides to make the maximum decrease in profit per standard bag, what will its total profit be? Well, we can, if they decided to implement that, we can very simply say, well, they went to 6.31, and let's rerun Solver. Total profit now will be 5675.40. That's the answer to question 3, 5675.40. Let's restore all base values before each question. Run this back to 10. Rerun Solver. Leave it there. Good to go. Okay, I'm going to set up another 15-minute recording session, and we'll be back